Hi team! For those of you that have been watching this series on regression, you know that all a regression is a way of describing the relationship between one dependent variable y and a whole bunch of independent x variables. But what happens if those x variables are themselves related? Well, that's multicollinearity, my friends. Come with me as we explore the concept.
Okay, so here we go for a deep dive into multicollinearity. All the other videos in the series on regression are up on zedstatistics.com. And indeed, we've touched on multicollinearity in the regression assumptions video. But here I'm spending just a little bit more time on some of these concepts. And I've also done something pretty special. I've created a little simulation of my own to give you a flavor of how multicollinearity actually feels, not just how to diagnose it and how to deal with it, but I'm going to give you a sense of how it actually affects a regression. Anyway, this is the plan of attack. We're going to have a look at the intuition behind multicollinearity. We're also going to assess why we'd bother caring about it in the first place. Is it a big issue? And what, in theory, is it doing to our regression? We'll then look at two different methods of detection, one via what might be called bivariate correlations, and a second where we look at variance inflation factors, which is a little bit more robust than the correlations method. We'll then see what happens once we've diagnosed multicollinearity in our model. What remedies are available will be assessed here. I'll then show you that simulation that I referred to earlier. Basically what I've done is I've created a data set and then infected it with multicollinearity to greater and greater degrees, and we'll see what happens to our coefficients and standard errors. And finally, we'll have a look and see what happens with perfect multicollinearity. All right, so we're ready to go. Let's dig straight in. So let's think about the following regression. Let's just say we're trying to assess a lawyer's salary as a function of their number of years of experience and also their age. Now, what a regression will try to do is tease apart the individual effects of years of experience and age on the lawyer's salary. But you're going to have to afford the regression the opportunity to tease apart those effects. Multicollinearity occurs when the x variables themselves are related, such that those individual effects become obscured. So this is the perfect example, right? The more years experience you get as a lawyer, probably the older you're getting at the same time, right? So this regression is going to have a tough time figuring out, well, was it your age increasing that improved your salary? Or was it the years of experience increasing that improved your salary? How can you really figure that out if these two work in lockstep? Now, another way of looking at this is to think about how we interpret these coefficients. So remember in my previous videos, to interpret the coefficient of, say, years experience, that's beta 1, you'd say that's the marginal effect on salary of one additional year's experience holding other variables constant. And similarly for beta 2, that would be the marginal effect on salary of an additional year of age holding other variables constant. Now, is it possible to really hold the other variables constant in each of these cases? Well, Janet down here is rightly cynical because, of course, you can't really hold your age constant as your years of experience are increasing. So that's a problem. And that problem is called multicollinearity. Okay, so why do we care about that? Well, let's have a look and see what it does to our regression results. So let's just say I've run this regression and we've got some coefficients here for experience and age. So these would suggest that for an increase in 1 year's experience, your salary is to increase by $3,000, $3,886 on average. Now for age, something similar happens. For an increase in 1 year of age, you're expecting an increase in about $2,000 to your salary. Now each of these coefficients has standard errors associated with them. And again, if you've seen my previous videos, you'll know how to interpret these plus the p-value as well. But what part of this output does multicollinearity infect? The coefficients themselves are still unbiased. In other words, they still represent our best guess or our best estimate as to the true values of beta 1 and beta 2 respectively. But they become quite sensitive. So maybe if you throw another variable in the mix here, these coefficients might jump wildly. But really what happens with multicollinearity is that it inflates the variance of the affected variables. So experience and age, if they're affected by multicollinearity, these standard errors are going to blow out. And indeed, they're quite high here, such that both of the p-values are reasonably high as well. And you'd know looking at these p-values that neither of these two variables seem to be statistically significant. And that might be surprising, right? You'd think that surely years of experience is going to affect your salary. Same with age. But it's almost like these two variables are fighting for the effect on salary, and they're kind of getting in each other's way because they're moving in the same direction. So the regression's having a tough time teasing apart beta 1 and beta 2, so these standard errors get blown out. And finally, it's probably worth noting that the overall model fit is not affected, so it only really influences this red section of your regression output. The R-squared, the ANOVA, and the F statistic, and also your ability to use the model for prediction is unaffected. So I guess in summary, all that's happening is that we become more uncertain about these coefficients. Or in other words, they just have a higher variance. Okay. So how do we detect it in a model? Well, the first thing we can do is check the correlations between all pairs of x variables. So let's just say we had 4 x variables. So instead of just years of experience and age, say we had 2 other variables as well. And let's just call them x3 and x4. You can check what's called the bivariate correlations between each pair of these x variables. And of course, we know that correlations go from 1 to -1. So you'd be hoping for something around 0 here for these correlations. For example, x1 and x2 here have a correlation of 0.91, which is quite high. But Janet's going to ask us a question: how much is too much correlation? And there's a general rule of thumb that says if the correlation is greater than about 0.9, this could start being a problem. But as I say, with all of these rules of thumb you'll get in statistics, there's nothing black and white about it. There's nothing magical about 0.9. In fact, there's a lot of sources that suggest that this is a bit too conservative. Correlations up to sort of 0.95 are still pretty cool. So if you're looking to me for a black and white letter of the law, what do I do with my correlations, you're not going to get it, because it really is a question of degree. And as we'll see when I do my simulation a little bit later, correlations of 0.9 and even 0.95 are not fatal to a regression model. We'll see how that works a little bit later. But let's have a look now at the second detection method, which is variance inflation factors. Now, as I said, this is a little bit more robust because unlike correlations, we're no longer looking at bivariate relationships between the x variables. We can actually do a little bit more here. So let's again look at a theoretical regression with y and 4 x variables, x1, x2, x3, and x4. The way to calculate the variance inflation factor for each of the x variables is to first create an auxiliary regression for each of the x variables. So let's just take x1 and we'll create what's called an auxiliary regression for x1. And that's where we regress x1 on the 3 other x variables. So y is nowhere to be seen here. It's just x1 being our new dependent variable and being regressed on the 3 other x variables. And what this effectively is trying to figure out is how much of x1 is being explained by the 3 other x variables. How superfluous is it in the original model? How much of its information is already contained in those three other variables. So of course we're going to have to try to find the R squared of this model, and the variance inflation factor for x1 would be 1 divided by 1 on R squared from this model. And this has got a subscript k here, just meaning it's the R squared from the kth auxiliary regression, right? So you'd run this regression, find the R squared, and then you could construct the variance inflation factor. And you would do that for the three other x variables as well. You'd put them in the hot seat in the dependent variable position and regress them against the three other x variables and see how they go with the variance inflation factors. And clearly the higher the R squared, the higher the variance inflation factor will be. But Janet's going to ask us this question again, which is how high is too high for the variance inflation factors? What number are we looking for? Is there a figure beyond which we're going to say, you know what, that's too high for our variance inflation factor? And of course, my answer is going to be the same. Yes, there's a rule of thumb, and typically people will say variance inflation factors above 10 are problematic. So in this case, if our auxiliary regression from x3 provides us with a variance inflation factor of 12, we might say that x3 is somewhat redundant in our original model. In other words, it's being explained by the three other x variables to a certain degree. But again, nothing special about the number 10 here. You'd always be using your judgment. Okay, so what do we do now that we've detected multicollinearity in our model? Option 1 is to do absolutely nothing about it. And believe it or not, that's typically what you're going to do. If your model is being used for prediction only, then the standard errors of the coefficients are not important. So long as the coefficients themselves are unbiased, which they still are, then you can use your model for prediction. Alternatively, if the correlated variables are not of particular interest to the study question, you can still use your model for everything else. So it's not as if this invalidates all the other variables in the model, right? The model's goodness of fit is still intact, so you can still rely on things like the R squared of the model and all that kind of stuff. And you can certainly look at other variables that aren't suffering from multicollinearity. No problem there. And also, if your correlation is not super extreme, you can still just do nothing about it and be reasonably okay. And we'll have a look and see how extreme the correlation needs to be for us to be forced to do something about it. So option 2 is to remove one of the correlated variables. So here you'd assess the actual variables and figure out whether they're providing the same information. Now, arguably, age and years of experience are providing subtly different pieces of information, right? But certainly there are some instances where two variables are giving you the same information, just in slightly different ways. And in those cases, you would want to remove one of those variables. But the problem with option 2 is that in trying to solve multicollinearity, you might actually be creating another problem, which is called omitted variable bias. Because all of a sudden you've got a variable that's outside the model now that might be pulling the strings still of the remaining variable that you've left in. So yeah, again, this is making option 1 look a little bit more appealing still. There are two other options as well. You can combine the correlated variables. Now this one's actually pretty good. So for example, in our years of experience and age scenario where we're looking at lawyers' salary, we could create something called a seniority score or something like that, right? Where we combine algorithmically experience and age. And that way both of those pieces of information are included in one variable that no longer suffers from multicollinearity. And the final option, which I have never used in practice ever, but you can use these things called partial least squares or what's called principal components analysis. Now I did find a good video on principal components analysis. I haven't done it, but the guy does it pretty well. It's long, but it's quite useful. So If you're a sucker for punishment, you can have a look at that, and I'll put the link for that video in the description. But really, as we'll find, that's probably only a resort in very rare scenarios. Okay, so here we get to my favorite bit, unsurprisingly, because it's my simulation. And as I said in the intro, this is where we're going to get a feel for what multicollinearity does to our regression output. So what I've done is I've concocted a data set myself of law firm salaries. So here we've got 10 employees, I guess you'd call them partners, right, at a law firm. And here's their salaries. These are Australian dollars, peeps. But still, they're on good coin. And here's the years of experience. So Frank's earning the big bucks, 250 grand per year, but he's been at his job for 27 years. Dennis is earning 180 grand for 22 years, etc., etc. So I created this data set myself. So they've got 10 observations in it, but that's okay. I'm now going to run this regression that assesses the effect of experience on salary. And we would hope that the regression output would tell us there's a positive relationship between experience and salary. And indeed, when we run a regression, you can see that the coefficient is 6014.8 with a standard error of 519. Let's highlight that. So the coefficient 6015, that indicates to us that for an additional year's experience, one would expect the salary to go up $6,000. Not bad. And the standard error is quite small, 519 in comparison, giving us a p-value that is less than 0.0001, so very, very small p-value, which is unsurprising because quite clearly experience is affecting the person's salary. Okay. Now what's going to happen here is I'm going to add another x variable. So our new regression equation might look a little bit like this, where we've got experience here again, plus another x variable I've thrown in. Now, it doesn't so much matter what this represents, but what I'm going to do in my simulation is simulate a new set of 10 values here for this x variable that is highly correlated with the 10 values from the experience variable. And then we're going to see how these figures change. Will the coefficient of experience change now that there's a new correlated x variable in town? Will the standard error of the experience variable, will that change now that there's a new x variable? And also, is it possible that this very, very small p-value can blow out such that experience is no longer even significantly impacting salary at all? So of course I'm going to be testing numerous strengths of association between x and experience. And I've tested where rho, which is the correlation, is 0.8, 0.9, 0.95, and 0.99. So I've run numerous simulations under each of these 4 conditions and then assessed how the coefficient and standard error of experience has changed. Juicy, right? Well, let's find out what happened. So there's the equation again, experience, and there's x, our correlated x variable with experience. Now this was the original condition where x didn't exist. So when there was no additional variable, the coefficient of experience was around 6015, if you recall, and the standard error, which is in black here, was 519. Now when I add that x variable that has a correlation of 0.8, it doesn't much change. The standard error increases a little bit. Don't forget this is the standard error of this coefficient for experience on salary. That coefficient stays about the same and the standard error only increases a little bit. Now when I ramp up the correlation between these two variables, this coefficient beta 1 still stays about the same at around 6,000. There's a bit of fluctuation because obviously there's a bit of randomness associated with these samples that I'm pulling with the correlation of 0.9. But conveniently, the standard error increases a little bit further. Now this is still quite a small standard error, respectively. The standard error here is only about a quarter of the coefficient, which still indicates a fairly low p-value here, suggesting that experience is still highly related to salary in this condition. And when you get to 0.95 with this correlation here between X and experience, the standard error is starting to creep up a little bit. And this is starting to become of sort of borderline significance. I think the p-value at this point is around 0.02. And finally, when we ramp up the correlation so that it's 0.99, so that's when X and experience are very highly correlated, you can see the ramp up in the standard error now. So this is empirically showing what I was telling you in the beginning of this video, that the coefficients are still unbiased in the presence of multicollinearity. So this beta 1 character didn't change very much, a little bit of fluctuation, but certainly no structural change given this correlation. But the standard error did ramp up significantly. And what actually happened at the end is that the p-value here is about 0.2, meaning that experience is no longer significantly affecting salary at this point. So clearly X and experience are fighting for significance in this model now, such that the model can no longer tease apart the effect of experience on salary. Now, I'll include the spreadsheet I used to conduct this simulation. I did do it on Excel for whatever reason. If someone wants to have a go at doing it using proper software, feel free and send it through to me. I'm happy to give you a little props in a video if you've done that. But just so you know, I haven't just concocted this out of thin air. You can download my handiwork. But I think that's pretty cool, and it gives you some visual impression of how multicollinearity actually affects your coefficients. And the other thing that's quite surprising is just how much correlation you need for things to become problematic. Even at 0.9, there's not that much of an issue, right? Now, of course, experience was very highly significant in explaining salary in the initial stage, right? So maybe this jump in standard error might be a significant jump. But when I saw this, I was definitely surprised at how little an issue these sort of mildly high levels of correlation really were. Anyway, thought that was interesting. Okay, so a final point to note about perfect multicollinearity. Now, you may have been looking at that plot in the last slide thinking, I wonder what happens if rho goes all the way up to 1 itself. Now, this would mean that the X variables are perfectly correlated. Well, if you try this using any statistical software, it'd give you an error message that says near singular matrix, which is basically software speak for computer says no. As soon as you have two variables in a model that are perfectly collinear, the whole model breaks down and you cannot get any regression output. Think about it. The model's trying to tease apart those individual effects, and you haven't given it any leverage to assess those individual effects. Okay, so that's all well and good, but are there examples, real-world examples, where this actually happens? And yeah, there are. Let's zoom in. Say I'm trying to assess the amount of energy burned by an Olympic swimmer when they're doing their swimming training. I can construct a model like this where the amount of energy, presumably in kilojoules being burned, is a function of, say, I don't know, whatever they had for breakfast, how much sleep they had the last night, blah, 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 blah. You'd also want to put in the total distance covered in their training session. That's quite important. And maybe also the number of laps that they've done. But that's no good, because the distance is obviously going to be the laps times 50. You can get from the number of laps to the distance covered using this straight formula. So there is no extra information being provided by the number of laps when you've already provided the total distance covered. So this is one of those scenarios where you would need to remove one of those two variables, and comfortably so as well, because they're providing the same information, just in different units, right? Meters or laps. What about this one? You're assessing the water pressure on a diver as a function of the meters they are from the surface of the ocean, and also the meters they are from the ocean floor. Now, is that a problem? Well, again, you can get from one to the other. The meters from the ocean floor is just the total depth of the ocean minus the meters they are from the surface. So again, these two variables would exhibit perfect correlation, such that the regression now suffers from perfect multicollinearity. And finally, we might get one that looks a bit like this, where we've got, say, sales as a function of, well, here B5, here our variable is the amount we've spent on advertising. But we also have what's called dummy variables here for whether we're in quarter 1, quarter 2, quarter 3, or quarter 4, being, say, the Christmas quarter, right? So if you're in quarter 4, you would expect sales to be higher. But if these indeed are dummy variables, 1 if you're in quarter 1, 0 otherwise, 1 if you're in quarter 2, 0 otherwise, etc., etc., well, quarter 4, Q4, can be expressed as a linear combination of the other 3. So I can say Q4 is equal to 1 minus Q1 minus Q2 minus Q3, because if it's in one of the other quarters, Q4 must be 0. And this is actually called the dummy variable trap. Remember how you're always told with dummy variables that you have to remove one of the categories and let that be your base case. Remember that? Well, the reason is if you include all of the categories, if you exhaust all of the possible categories as dummy variables, that final one will be causing perfect multicollinearity, and your regression shuts down. So there you have it, team. Multicollinearity. Pretty deep, right? Well, you asked for it. If you like the video, feel free to subscribe. I've got heaps of others on zedstatistics.com on regression, but on a whole bunch of other things as well. I also do a podcast. And if you've got any suggestions at all, feel free to send through an email on the website or just make a comment on the video and I shall reply. See you around.